We continue our lecture on primes and the greatest common divisor, and we begin at our discussion with the Euclidean algorithm. Before describing the Euclidean algorithm, we will show how it is used to find the greatest common divisor of 91 and 87. First, divide 87, the larger of the two integers, by 91, the smaller, to obtain 287 is equal to 91 times 3 plus 14. Any divisor of 91 and 287 must also be a divisor of 287 minus 91 times 3 equals 14. Also, any divisor of 91 and 14 must also be a divisor of 287 equal 91 times 3 plus 14. Hence, the greatest common divisor of 91 and 287 is the same as the greatest common divisor of 91 and 14. That means the problem of finding the greatest common divisor of 91 and 287 has been reduced to the problem of finding the greatest common divisor of 91 and 14. So we find the greatest common divisor by dividing 91 by 14 and find that 91 is equal to 14 times 6 plus 7. Because the common divisor of 91 and 14 also divides 91 minus 14 times 6 is equal to 7, any common divisor of 14 and 7 divides 91. And it follows that 91, the greatest common divisor of 91 and 14 is equal to the greatest common divisor of 14 and 7. Continue by dividing 14 by 7 to find that 14 is equal to 7 times 2. Because 7 divides 14, it follows that the greatest common divisor of 14 and 7 is 7. Furthermore, because greatest common divisor of 287 and 91 is equal to the greatest common divisor of 91 and 14 is equal to the greatest common divisor of 14 and 7, which is equal to 7, the original problem has been solved. Lemma 1. Let A equal BQ plus R, where A, B, Q, and R are integers. Then the greatest common divisor of A and B is equal to the greatest common divisor of B and R. Example 16. Find the greatest common divisor of 414 and 662 using the Euclidean algorithm. Well, you can see what I used here is an Excel to rapidly find this, and what we found was the greatest common divisor is 2. Because 2 is the last non-zero remainder. So here's our Euclidean algorithm, and I've given our author's presentation, and I've also given the recursive technique in C++ as well. GCDs is linear combinations. The greatest common divisor of two integers a and b can be expressed as SA plus TB, where S and A are integers. In other words, the GCD of AB can be expressed as a linear combination with coefficients A and B. For example, GCD of 614 is equal to 2, and 2 is equal to minus 2 times 6 plus 1 times 14. Theorem 6. If A and B are positive integers, then there exist integers S and T such that the GCD of AB is equal to SA plus TB. Definition 6. If A and B are positive integers, then integers S and T such that GCD of AB is equal to SA plus TB are called Bezout coefficients of A and B after Etienne Bezout, a French mathematician of the 19th century. Also, the equation GCD of A comma B equal SA plus TB is called a Bezout identity. Example 17. Express GCD of 252, 198 equal 18 is a linear combination of 252 and 198. So what we do is we, to show that GCD is 252, 198 is Euclidean algorithms uses these divisions, and you can see them on your screen. Using the next to last division, the third division, which is this one right here, we can express the GCD of 252, 198 equal 18 as the linear combination of 54 and 36. 18 is equal to 54 minus 1 times 36. The second division tells us that 36 is equal to 198 minus 3 times 54. Substituting the expression for 36 in the previous equation, we can express 18 as a linear combination of 54 and 198. So we finally arrive at 18 is equal to 4 times 54 minus 1 times 198. The first division says that 54 is equal to 252 minus 1 times 198. And substituting the expression for 54 into the previous equation, we can express 18 as a linear combination of 252 and 198, which was our goal for this example. And we get 18 is 4 times 252 minus 5 times 198. Lemma 2. If A, B, and C are positive integers, then such that the greatest common divisor of A and B is equal to 1, and A divides BC, then A divides C. Lemma 2 is used in the proof of uniqueness of prime factorizations stated in lemma 3. Lemma 3. If P is prime and P divides A1 times A2 times A to the n, where each A sub I is an integer, then P divides A sub I for some I. It can be shown that a factorization of an integer into primes is unique. Any positive integer n can be written as the product of primes. P n is equal to P1 times P2 times P sub s, such that P1 is less than or equal to P2 is less than or equal to P sub s. Example 18. The congruence 14 is equal to 14 is congruent to 8 mod 6 holds, but both sides of this congruence cannot be divided by 2 to produce a valid congruence, because 14 divided by 2 is 7 and 8 divided by 2 equal 4, but 7 is not congruent to 4 mod 6. Theorem 7. Let M be a positive integer and let A, B, and C be integers. If AC is congruent to BC mod M and GCD of CM is equal to 1, then A is congruent to B mod M. And that concludes our lecture.